Sounds awesome. Santa Claus.
All right. Hello, everybody. Thanks for coming back. Today we'll actually get into the interesting parts, actually do some math and look at some code and all the good stuff of deep learning. Before we get into the content, again, if you have any questions, just feel free to raise your hand. I will, like I said, err today on the side of boring some people, but making sure everybody is on board with the very simple and most basic sort of Lego piece of a pretty large eventual architecture. So we'll really go again over the chain rule and things that hopefully you still all remember, but in case it's been a while, we'll very slowly go through that. We'll actually work a little bit on the whiteboard, so if you want to take notes, might want to get out your pens. Last time I was asked whether you need to really know natural language processing and details of linguistics because of the slides. Those kinds of slides were just there to give you an idea of what kinds of things deep learning contrasts with, and to really understand and appreciate how simple it is compared to all the other ways you could do and solve a lot of these other tasks. So it's recommended. You'll appreciate more how awesome this is and how much it simplifies, how much deep learning can simplify these kinds of tasks, but it's not required. Also, I had a couple of questions about people asking if they could have their final project with things that aren't necessarily natural language. And so in general, I love these kinds of techniques because they're so broadly applicable. So if you want to use deep learning for other kinds of language processing and that isn't natural, that's okay. So you could have genetic language and genes. You can have programming languages. These techniques are really very, very broadly applicable. So just let us know and to make sure it's reasonable, but it very likely is. I'll try to have the slides before. We had a couple of questions. It's a little tricky. Sometimes I don't have them before. So I'll try my best to try to upload them. We had them today like an hour before. That's hopefully the minimum or the maximum going forward. Yeah, so we'll have a little bit of whiteboard. And also we have a new TA, thanks to the high enrollment, Namrata, right down here. She'll update a new, we'll have an additional office hour for one of the days. We don't have an office hour yet. All right, are there any organizational questions? All right, then let's get started. So I briefly alluded to this, and I just want to go again. Today we'll talk mostly about word vectors and words. And before we just accept the fact that word vectors are a super optimal and great way to represent words, let's think a little bit about alternatives that have been really used by pretty much 95% or so of the natural language processing community and in most previous work. So we can look at the definition of the meaning of a word. According to the Webster Dictionary and their first sort of brief summary, it is the idea that is represented by a word or a phrase, or another alternative meaning is the idea that a person wants to express by using words or signs. So now we're including signs. So even if you can't speak, you can still try to express a meaning. And the third one is the idea that is expressed in a word of writing or art. So then, includes art. And so if you just quickly read those might all sound kind of similar. But really, one is about the meaning that's inherently represented in a word. And another one is the desire to represent something. So just because you think you want to express something, that doesn't mean the person that gets, that receives your information will have the same understanding of the meaning that you try to convey. And then so basically you have the representation that is being received. So again, there's a lot of very interesting linguistics and philosophy. They're so-called Greichen maxims that try to understand really how do people interact and how do people talk to each other and so on. A lot of those are very hard to formulate in computation. And so we'll only go through one example of an alternative representation, which is basically trying to represent words and their meaning in terms of a taxonomy. So a taxonomy is basically a very large graph, and in the case of Wordnet, which is one of the most commonly used taxonomies, it's a DAG, a directed acyclic graph, that defines a lot of relationships between words. So you have, for instance, one of the most important one, the is-a or the hypernym relationship, defines sort of a general term. So we can look at panda, for instance, and look at the first meaning of the noun panda, and then we can ask in very simple Python code, what are all the words that generalize panda? So, you know, we have a carnivore, placental, mammal, vertebrate, chordate, animals. These are all words that subsume panda. So panda is just a subset of all the things that are vertebrates, for instance, or animals. And it goes to organism, a living thing, a whole, an object, a physical entity versus, you know, a theoretical entity like an idea or love or something like that. And then everything in this taxonomy ends at entity. So everything, according to Wordnet in the world, is some kind of entity. And of course, you know, there you could have a set of all the things that are green, and that might be, you know, have different subsets. So it can't just be a tree structure; it has to be a DAG. Another thing, sort of information that Wordnet gives you are so-called synsets, or synonym sets. Here we have a couple of the different meanings of the word good. So you might say good is, you know, honorable, respectable kind of good, or it could be the just good, this is a good law, or the, you know, this is an expert, good practice, proficient, skillful kind of good, or, you know, my good friend, my dear old friend, or something like that. And basically inside this taxonomy, Wordnet assumes that the meaning here is completely identical. These are synonyms. So what are some problems with this kind of both discrete representation and trying to formulate all of that in this taxonomy? Well, one, you're really missing a lot of nuances. So according to Wordnet, good is basically a synonym for one of its meanings with expert, practice, proficient, or skillful. But would we really use the term expert interchangeably with good? Probably not, right? So it's missing a lot of nuances, and also there are only so many people who could work on this project of setting up the taxonomy and, you know, keep it up to date. And so it's basically impossible to keep it up to date. So you may have a bunch of other words that people might think are good, like wicked, badass, nifty, crack, ace, or the Silicon Valley ninja. So if you're a ninja coder, you're a very good coder. And so those are obviously not in Wordnet. And it's very hard to keep it up to date. So ideally, we would learn our vector representations or our word representations from data. We just give it more data, it reads continuously the news, and it starts learning about new words. That will also make it in some ways less subjective, right? Because there's some person eventually who has to acknowledge the fact that this word means exactly the same as this other one. And it also requires a lot of human labor. And this is true for a lot of other of these kinds of discrete representations that we have. So you have, for instance, Wordnet for English, but Wordnet does not exist for every other language that is out there. In fact, the majority of languages don't have a group of people who sits there and tries to write a taxonomy for that language. It's also very hard to compute, and this goes to the first part of the missing nuances, word similarity. So let's see what this kind of representation leads to. Basically, the vast majority of rule-based and other kinds of statistical NLP models and systems regard words as atomic symbols. So you might say hotel, conference, or walk are all just an index in a very large, very sparse vector. We call these often Onehot vectors. So here you might say the word hotel is basically a gigantically long vector where, you know, the 536th entry is a 1. And that means the word hotel is basically that entry. And the dimensionality of that increases the larger your vocabulary is. And so for really, really large text corpora, like a terabyte of size, you have 13 million different specific words. And so the main problem here is that when you represent a word just as an index, and then, you know, you might have a feature later on in a logistic regression or something, you don't get any notion of similarity from this kind of representation. So motel and hotel, if you wanted to, for instance, compute inner product, just multiplying all the numbers and summing them up, is 0. Just like motel is, you know, 0 with cat and every other word in the vocabulary. And of course, that's not ideal, because we have some notion that motel and hotel are actually quite similar kinds of things. So the main idea of today's lecture and of almost all word vector kinds of representation is to instead use the neighbors of a word to represent that word. Or according to Firth, you shall know a word by the company it keeps. And this is really one of the most successful ideas of modern statistical natural language processing, and it does permeate into deep learning. So instead of saying banking is just this discrete thing, we're going to try to represent banking in terms of, in this case we look at two windows around the word banking in the large corpus, and we'll try to describe it somehow in terms of government debt problems turning into crisis as has happened in. So that leads us to the natural question: how do we actually try to represent a word in terms of its neighbors? And the answer is with a co-occurrence matrix. So there are two options that we usually have to create this co-occurrence matrix, and we'll go into one of them in the next couple of slides. The first one that we won't go too much into is to just describe co-occurrences in terms of words appearing in the same document. So you have a vector for each word, and you have basically the number of documents here, and here you have the number of words, and each line here is for a specific word. Does it appear in this document, that document, and this document? So that kind of representation that just looks at whether a word appears in the entirety of the document will not have any notion of part of speech tags. So you might say all sports terms will create roughly similar kinds of vectors, and sailing and swimming and wet and boat, they're all kind of similar if you don't look at the local context. And so another representation that we'll use a lot more in this lecture and throughout the whole class is to actually look at windows around the word. So instead of just taking the entire document as the context, we will only look at the words, like the 5 words to the left and 5 words to the right, just like we described right here. So let's go through an example to give you some intuition of what this actually looks like. So let's assume for now our window length is 1. So for every word we will only look at the leftmost neighbor and the right nearest neighbor. And let's also assume for now that we have a perfectly symmetric, we don't really care if the context words, the neighboring words are to the left or to the right. And to keep it simple, we'll just have 3 words in our entire corpus from which we want to learn the word vectors. The 3 sentences are: I like deep learning, I like NLP, and I enjoy flying. So let's look at what a window 1 length co-occurrence matrix would look like. So here we basically say, all right, for I, in the context of the word I, to just 1 word to the left, 1 word to the right, I see like twice. Let's assume for now that there is no beginning of sentence token, so we just kind of ignore the first word's left neighbor and just assume there is none. And then we also for I have enjoy. So like and enjoy are the 2 neighboring words for the word I. And for like, the 2, like has in its neighborhood and in its context windows twice the word I, once the word deep, and once the word NLP. Right, so like here, NLP and I, deep and I, and so on. So we can basically go through the entire corpus, and for each word find what are the words to the left and to the right, and we keep a count. Fairly straightforward. Are there any questions about this so far? Cool. All right, so we could now say, well, we're done, right? This is a vector, and in some ways it does capture that like and enjoy are actually more similar, right? They have a big overlap here, whereas enjoy and deep has no overlap. So this is 0, and enjoy and like are more similar. So we actually have a vector representation now that gives us some notion of similarity already. However, that kind of vector representation increases with the size of our vocabulary. So if we have subsequent models that we train on top of it, they change all the time. So that's suboptimal. And also, when we have 13 million potential neighboring words, that representation gets gigantic and it's very hard to store and so on. And also, we'll run into a sparsity issue where if we try to eventually estimate statistical parameters on top of these words, and you have 13 million times 13 million, it's going to be very, very hard to train any kind of model on top of that kind of co-occurrence matrix. And that leads to less robust models. So the solution to that is to actually try to create low-dimensional vectors from this very large sparse matrix. The idea here is to basically try to store most of the important information in a fixed small number of dimensions. And that will result in a dense vector representation. And when we say small, it's a pretty broad range between 25 to 1,000 usually. And that depends, again, on your task. For simple tasks like finding named entities like locations and people, you might get away with 25. If you want to solve all of machine translation, you better have 1,000. So that leads us to the question, how should we reduce the dimensionality from having this large co-occurrence matrix to smaller dimensional vectors? And fortunately, in the last lecture, you all mentioned, or most of you raised your hand when I asked who knows singular value decomposition, or SVD. And that is essentially the technique that we can use here. So again, we can represent the original co-occurrence matrix and find a best rank K approximation to that in terms of least squares using SVD. And so again, just as a refresher here, you'll have your left singular vectors here, basically orthonormal columns, and here you have orthonormal rows, and along the diagonal of S you'll have all your singular values that basically, if you order them, you'll get the most important axes of variation in your data in the first column here of U1. So what does that look like? That sounds kind of theoretical. How do you actually use that to get a word vector? So again, let's just look at some very, very simple code. Here, I just manually put in our co-occurrence matrix. Obviously, you'd want to write a little script that goes in little windows over and tries to collect the counts of which words are neighboring where. This is, again, the same corpus that we had before. I like deep learning, I like NLP, and I enjoy flying. And this is the entirety of our vocabulary. Now, all we need to do is we fire up NumPy and its linear algebra library and call SVD on literally just that matrix. That will give us our left singular vectors. So this matrix of vectors. S here is just the diagonal, essentially, of the matrix S, so it can be represented as just a vector, and V. So now, this is literally all we need to do to get the simplest type of word vector representation that is low dimensional. So we mentioned here that for each word, we're going to use the K first elements of the left singular vectors. And we essentially can visualize this in 2 dimensions by just taking the first 2 elements, the biggest axes of variation inside our low dimensional space. And what we'll observe is that we'll actually capture a lot of the similarities. A lot of what's going on here in this vector space is very intuitive. So for instance, like and I are probably the 2 most frequent words in the corpus. And so some notion here is captured of frequency in one of these axes. We also know that like is in some ways most similar to enjoy because it's something that you can do. So I like, I enjoy. So the nearest neighbor of like happens to also be enjoy, which is again very intuitive. It's trying to capture here the most important information. You can say enjoy and learning are similar because they both are roughly in similar places, but most similar to learning is actually flying. So flying and learning both happen to appear at the end of sentences, and hence they're very similar. Are there any questions about this? Yeah.
Like it seems that we have thrown away the singular values here. Like, do the singular values represent anything?
That's a great question. You can actually, in fact, multiply your U vector by the inverse of S and then try to incorporate that. It's essentially a hyperparameter, and some people used, like for a long time, people used to do it. Now actually people found that it doesn't help that much for a lot of downstream tasks. So the simplest one is just to take U. Great question.
Second question is that, so like it seems almost magical that like I can enjoy her nearest neighbors. Like what made them nearest neighbors, or like is there any more intuition to that? Or?
I mean, so, in some ways it's magical. In other ways, they are already kind of similar when you look at just the co-occurrence counts, right? They actually have similar co-occurrence counts, and you're just trying to capture here the largest variations in that matrix. And so, in that sense, it's not that magical that they also end up similar in the low-dimensional vector space. But honestly, there will be some things here that will eventually, at the end of this lecture, feel kind of magical. Because you can take, eventually, the vector of king, subtract the vector of man, and add the vector of woman, and actually get to the vector of queen. So there's some crazy stuff that happens. And for a year or so after that came out, people thought, wow, this is like dark, deep learning magic. And eventually, we actually had a paper, Jeffrey Pennington, me, and Chris Manning, where we actually give some explanation of why these things happen. And it's, again, boils down to statistics. Yeah.
And the distance we're using is Euclidean, but shouldn't it be cosine distance?
That's a great question. In fact, some of the similarities, it helps a lot to use cosine distance. In other cases, the best one is actually just a simple inner product between the two, and use that as your metric. And Euclidean can sometimes also actually work. And that is where there isn't as good of an intuition. People just try different distance metrics, and some work better than others. Great. OK, so just to reiterate this, in all the subsequent models from now on, including all the deep learning models, a word will be represented as this dense vector. Of course, nothing is as simple as I just described it in the very first iteration. So really, when you create this entire matrix, and you have function words like the, he, and has, so words that there are only a finite amount of them, so there are only so many personal pronouns, there are only so many determiners like the, they're way too frequent in the data set. So basically, in terms of frequency statistics, we have the so-called Zipfian law or power law, where basically certain words appear very, very frequently, like the is the most frequent word of the English language. And then all the interesting words, like panda and ninja and whatnot, they're actually rarer and rarer in any corpus that you can have. But those really actually capture a lot more of the semantics. So instead of allowing just taking the raw co-occurrence matrix, you actually have to do some hacks to improve it. So basically, one of those is you just cap the maximum number that you have in this matrix. So instead of taking all the counts for the, you just say the maximum count that we can have in the matrix is 100 or 1,000. That way you kind of cap and don't allow these function words to kind of determine the meaning of all the other words. Because what that will eventually lead to is more syntactic representations. You just realize, oh, the always appears in front of nouns. And if the most important thing about each noun is that it appears after the or a, then maybe you'll just cluster all the nouns and you will lose some semantic information. The other alternative is to just ignore all the function words when you collect the nearest neighbors for all the other words that aren't function words. And there isn't really a very sound mathematical reason of like, you do this or this. You kind of try, you gain intuitions, you play around with these models, and then you pick what works best. Another technique that works very well for these kinds of SVD-based methods is actually to have a ramped window. So you could say that if I have several words here, then the first word here has a count of +10, this one +9, and it keeps going down. And the further away you are, the less important you are to describing that word. And so your co-occurrence matrix isn't just raw counts, but counts with a weight on them. And one of the most powerful things you could do, or most powerful transformations to the matrix, is actually to use Pearson correlations instead of the raw counts. And so the Pearson correlations, of course, will be negative for most words. Most words don't appear in the context of other words. And it doesn't really tell me that much about a panda that it doesn't co-occur with like an F-16, right, or a nuclear bomb. And so what you could do instead, and again, this is an intuition that's kind of intuitive and makes sense, but we'll have to actually play around with it and practice. And basically what that led to is to just set all the negative correlations in this large matrix then to 0. And then you really only care about the things that actually co-occur next to the word. OK, so here are some interesting first results when we use these kinds of SVD-based methods and try to then find nearest neighbors of specific words and just kind of do a hierarchical clustering. And it's pretty cool. So we can see here that wrist and ankle and shoulder are most similar in the resulting vector space, and eye and ear and face are closer to one another. And then in a completely different part of the space, you have sort of a bunch of countries clustering together, and in some ways here, different continents first cluster together before they combine with languages, and different cities that are more similar, closer to one another, obtain similar vector representations with these methods. What's also kind of cool is because we have these windows, we're actually capturing syntactic information or grammatical information. So we have here, for instance, take, taken, and taking are very close to one another in the vector space in took. And show, showed, showing, and show are also very close to each other. And this kind of gives us some hint that maybe we can get away with using vectors to even capture grammatical information. Right? We didn't have to tell the model about different tenses of verbs, yet it kind of learned that these should go together. Yeah?
Is there intuition behind why semantic similarities show up with these methods?
Yeah, so basically, so there's a very long answer that requires a long derivation, but the sort of intuitive answer is similar words appear in similar contexts. So when you look at Germany and France, they're both in the European Union. So their counts in this matrix of words will be such that here's Germany, here's France, and maybe there are other words in the corpus such as EU and central bank and whatnot. And so both of those will actually often have similar kinds of meanings. And in fact, when you look at king and queen, you will see that king appears in certain, lives in a castle, queen lives in a castle. But then there are a bunch of things that are more likely to be done by males and kings back in the day. And so you might take away some of the counts from this and add some others and gain some intuition now.
But with the things like shown, showed, showing, does that also hold in terms of the Cooccurrence things?
Yeah. But there, it's more about the local windows, right? You might be more likely to say, he showed in the past. And now in the past is something that is very similar and modifies all the other past tense verbs in similar ways because it appears in the same context. And so you're more likely to put past words and push them into the similar direction of the vector space. But what you see here, and this is what led us to, will lead us to the next technique, is actually that it's not as great as it could be. So shown here is in the top left, but take here is sort of the top word for that group. And eat up here is also at the top, but stolen is at the top here. So what we ideally would want is to have something that will have a similar structure. So show, shown, showing, or take, taking, taken, or something like that will all have a similar kind of geometric structure. So we could just say, hey, what's the past tense for that verb? And that will always lead us to doing the same vector operation. And that will actually happen in the next model that we'll go through. So before we go there, one last slide on sort of interesting patterns that emerge here. So you have, for instance, swim and swimmer, and teach and teacher, and learn or treat and doctor here, and pray and priest. So even verbs and their semantic sort of noun counterparts have a similar shared structure. Which is kind of amazing, right? We didn't tell this model anything about the world, about that certain professions participate in certain activities or anything. It just fell out of the statistics in the model. Okay. However, not all is great in SVD land. So the main problem is that the computational cost here scales quadratically for either these n by m matrices where you have words by documents or word by word matrices, right? If you have 13 million words, well, good luck trying to invert these matrices and so on. And so you'll have basically a quadratic cost here in the larger, the smaller dimension, and the smaller dimension is still really, really large. So it's very tough for having, when you have millions of words or documents. It's also very hard to incorporate new words or documents. So let's say I just have one new word, and now I want that word to only modify some subset of the words and not all of them. But the SVD operation is a global operation on the entire matrix. And there are obviously some ways you can try to do iterative methods, but those are non-trivial either. And so basically you'll have also, and that is one that is kind of aesthetically pleasing for the next methods. You have basically a different learning regime for SVD versus deep learning methods. And deep learning methods will most likely look at a specific example and then try to learn something from that example and then move on to the next one. And the methods that we'll now talk about basically will try to do that. They will try to learn the low-dimensional word vectors directly from the data and from each single example. In some ways, again, deep learning is a new term, but this is a very old idea as well. So it started in 1986 by Rumelhart and Hinton and others, where they're trying to learn representations by backpropagating errors. And backpropagation is an algorithm that we'll talk about a lot. It is essentially just the chain rule applied to very complex functions. And to renew today, we'll actually go through the chain rule and everything in all its gory details. I think I would personally attribute Joshua Bengio and his 2003 paper to really make this idea work in a large-scale setting. In a language models basically just try to predict the next word, and this is also something we'll go through in the class. And then Colobert and Weston actually had a paper that was very influential for me personally for my PhD, that had basically natural language processing almost from scratch. So they tried to solve a variety of different tasks, mostly of the simpler variety like part-of-speech tagging, named entity recognition, and things like that, but using the same model and showing that we can really learn these word vectors jointly with various tasks. And in fact, Jason Weston will also be a guest lecturer on the later parts of the class. He's done a lot of really cool work in this space. A much more recent and actually even simpler and faster model than all these is the so-called Word2Vec from Tomasz Mikolov. And that is the model. It's very simple, so it's really great for us to get our eventually backprop chops and our taking derivatives chops up and running. So that's what we'll start now. So the main idea of Word2Vec is, instead of capturing co-occurrence counts that you collect globally for your entire corpus, you will just try to predict the surrounding words of every word. So instead of keeping all the counts first, and this might be actually a negative, it will, for specific context words, try to say, given that I know this word is in my context, could I try to now predict the two words to the left and the two words to the right? It turns out that when you're trying to learn a vector representation that predicts other vectors, or the identity of other words, there's actually a very interesting and deep mathematical connection to trying to capture the counts. So in some ways, they are actually quite similar. And there's a really good paper by Jeffrey Pennington that introduces another method, which we'll go over after Word2Vec, that shows this connection. But basically, this kind of model will be very fast and will allow us to easily incorporate new sentences, documents, or even adding new words to the vocabulary in sort of an online fashion. So the model can keep learning more and more, and you just give it another document and it just gets a little better. So let's do some math and have the first equation of the class. And no worries, we will go through that in a lot of details, and I'm sorry, I will probably bore a lot of you, but I want to make sure we're all on the same page, and there may be some tricks that you will still learn even if you already know how to do these. So what do we try to do? Again, we're trying to predict these surrounding words. So we'll go through, and you can kind of see this as a temporal thing. For each time step, so this is time step 1, time step 2, time step 3, you will go and take a window. You'll go through and take the center word here. So at time step t, we'll assume you have a probability for all the context words given that you have the current word in the center of that window. And oftentimes the window size is around 5 to 10. And so this part here, we will just basically sum over all the time steps that are up to c many time steps away. Right? And we ignore the actual center word, because that's the one that we're conditioning on. Okay, so now, of course, the next question is, well, how does that give us vectors? And what is the actual representation, the actual function here for computing this probability of a context word given the center word of a window? Again, this is basically, let's say we have c equals 2. We basically have this as our window. And we have a time step t now. We're trying to predict, t minus 2, t minus 1, t plus 1, and t plus 2. All right, so in order to do that, we will basically define the following function. And this one is directly from the original paper, which we'll also have posted already and maybe highlight again so you can read it yourself. This is the original equation in the paper. And we'll walk through that now and try to derive and try to see how we can learn that so that you, at the end of this lecture, could actually go and implement it in Python. So in order to compute the context word here, they define this as the outside word, and they have the inside word here. And that will essentially be an inner product. And one very important note here is that they will actually have a different set of vectors for input and output vectors. A different set of vectors for input and output words. So right now, if I look at this window, I will learn a word vector for an input for this representation as an input word, and I will update the output words here. Once I move to the next window, right, so now this will be, we have a new word here at time step 4, time step 5, so this would be here time step 6. Now, what used to be a vector set that we learned for the inside word will now be an outside word. Okay, so every word is basically represented in terms of 2 vectors. And this is basically a hack. You could actually get away with having the same vectors there. Turns out it works better if you separate them out. It's a much easier objective function to optimize. Okay, so we have 2 sets of vectors for every single word, and we're trying to optimize this function here. So the primes are the output vectors, and WO is the identity of that word on the outside, the context word, and the inside word, WI, has a vector V. So this notation is kind of messy, so we'll rewrite this notation a little bit, and I wrote that at the top, at the left here, and we will now go through deriving that together. And basically, just to warn you, this will probably bore some of you, and we'll go as fast as your participation will allow. So if you're bored, just raise your hand more quickly, and we'll be done more quickly. But I want to make sure we're all on the same page. So here's the main equation, right? And I'm going to simplify the notation for you. So you have an output word, and you have the center word. And those are word IDs, so not vectors. And the way we will define this probability, and again, we want to, for now, let's assume we want to learn and update our center word vector. Our center word vector is VC, the vector of the word C. And so we'll take the derivative of this function with respect to this vector. So now, what is the probability? That's exactly how we define it here with the so-called softmax function. The softmax function, this whole thing, when you sum up all the u for outside vectors here, you basically will sum to 1. Okay, so then instead of taking just the probability, we'll actually take the log probability. So let's just define. So this part here is that part there, right? It turns out the log will make all our math a lot simpler, and it actually optimizes the exact same, will give us the same argmax. Right? It's a monotonously increasing function. And our probabilities are always larger or equal to 0. So now, basically, we defined this function. Are there any questions about this function so far? Yes?
Is there any notion of like how far away from the center word?
It's a great question. None right now. We could actually add here matrices and stuff like that, and that is a good idea and has been tried. But right now, all the outside vectors, so UO, doesn't matter where they are. Anywhere in the context around the center word C. Any other questions for that equation? All right. So now when we try to take the derivative of the log of this monster, what might be a simple first step to make our lives easier?
Subtract the denominator.
Exactly. So we know that log of a divided by b is log of a minus log of b. So let's write that out. So that is the log of the exponent of UO transpose times VC minus the log of the sum over w equals 1 to w of the exponent of UW transposed VC. All right, now we know that the derivative of a sum is the sum of the derivatives. And we also know that the log and the exponent cancel each other out. So let's define this as 1, and this here without the minus as 2. So now let's take the derivative of simply 1. And this is how it's the lowest we can go. UO transposed of VC. So what's the derivative of that? UO. Exactly. What? UO, exactly. So basically, if that is a trouble, I guess I could go one level lower, which is, what is this? This is just the sum over UO, the ith element of that vector, times VC, the ith element of that vector, for 1 equals 1 to n. And now you just take derivative with respect to VCI, or let's do a different one, VCJ, and that will just be UOJ. And that you do that for every single j, you get a vector back. All right, this is the lowest we could go. You should get that. That being said, it is actually eventually going to be a good idea to maybe write down single indices, because eventually we're going to have 5 different matrices W, and they have sub-indices, and eventually we're going to have tensors with W, I, J, and K, and they're going to be in some crazy recursive function in a tree structure, and at that point it actually gets kind of gnarly, and you do want to maybe write down what the derivative is of a single element of your matrix or your vector. All right, but let's assume we didn't have to include that. All right, so now we have the first part of our derivative. Now let's look at the second part, which is a little more complicated. And there again, we're going to do a little refresher on the chain rule. Again, in theory, we could just look at this and write down the solution. And at the end of this class, you hopefully will all be able to do that. But in the beginning, it's good, and especially once we have very complex functions that take different pieces, and you might have, a softmax error plus some other error coming in, it's good to think of the chain rule. So let's define some notation to make things consistent. So let's assume log is the function f, and this thing here is a function g of vc, and we can also define g of vc as just z. So now we could rewrite this as, let's ignore the minus for now, but let's not forget that we have it. So we'll have the derivative of vc is basically of f of g of vc. And again, this part here is z. So I'm not trying to confuse you by introducing new notation, but this is how we'll refresh the chain rule, which will be very useful in the future. So now, what is the chain rule? Yes? Exactly. So you should all look up the Wikipedia entry of the chain rule if you could not just write that out. This is really the most basic calculus from high school. but it can be rusty, and maybe some people have worked in different fields for many years, so we'll go through it. All right, so now we can basically take the derivative of this, and now we just need to know what is the derivative of log of z with respect to z.
1 over z.
Exactly. All right, so and z was basically just this sum. So basically the first element that we have here is 1 over this gigantic sum. So we have w equals 1 to w, where capital W here is the number of all our word vectors together. And we take the exponent of uw vc. Okay, any questions so far? Okay, so this part is this one right here. So now we multiply that with the derivative of z with respect to vc, and so, or partial d is what you can also call this. So what was z? So let's just write that out again. We'll have here vc, and z was basically just a sum. So this sum here is w, and here actually now the first element of confusion is if you use the same indices. And this is trivial, but if you use now the same indices here, you'll eventually get confused. So whenever you have a new sum, let's add a different index and just write here x. X will now sum over all the words in this sum, and w, small w here, will sum over all of these. All right, so let's write that down. So that is just exponent of u x now transposed vc. All right, so now we can define what is the derivative of the sum. Exactly, it's the sum of the derivatives. So let's now define this thing here. Just look at that, and we'll keep around all the other stuff, but we don't want to have to copy that in the board all the time. So let's just rewrite the sum of derivative of the sum as the sum of the derivatives. W All right, now what is the derivative of the exponent of something? Exactly. So we can now, and again, this is again just a chain rule, right? We have here a function f, we have some other function g of vc, which just happens to be an inner product, and we basically just apply the chain rule. Chain rule is derivative of the outside times next one, so we'll just write here, let's not drop our indices. Otherwise, we may get confused with the w later. We have the exponent here of u x transposed vc times the derivative of vc of the inside of that function, which happens to be ux transposed vc. So now, what's the derivative of that? ux. So now, we're basically done, and we just need to put them all together and not make an accidental mistake. All right, so now we have this part. So now let's put all these things together. So we have here, the very beginning, we had uo. So and this is again the full derivative with respect to vc of the log probability of P of O given C. So that is equal to UO minus, and now we had the first part here, 1 over W equals 1 to W of X of U W transposed VC times, and now here we have the sum of x equals 1 to w x of ux transposed vc times ux. All right, so what do we see now? So we could kind of try, this looks kind of unpleasant, and maybe we want to simplify it in terms of things we may have already computed before.
The denominator is a normalization constant.
Correct. So the denominator here is actually the normalization constant that we happen to have in our very original definition of the probability for a word given its center, or an outside word given the center word. So what else do we know? If you have, this is essentially just a single number, right? Inner product, single number, you sum exponent, single number, just sum up a bunch of single numbers. So what could you do to this sum to maybe try to simplify things?
Basically, you have exponent ux times vc divided by the normalization constant, which is the probability of vc.
Exactly. So now we could actually we could pull this number here into this sum. So you can write x equals 1 to w of the exponent of ux transpose vc divided by the sum over w1. And now again, this is very important to have different indices, right? Trivial but important. Times the exponent of w transpose vc times ux. And see, every single step is very easy, but you still need to put them together in the right way. And eventually all these will have indices, and you're going to have to program it. If you mess up one index, none of your programs will be right. All right, so now Arun had the good insight that this expression actually looks very, very much, basically exactly like this expression, but with a different index. Instead of UO, you have UX, which you just sum over the entire vocabulary. So we can rewrite this as UO minus the sum over x equals 1 to w of the probability of x given the center word times ux. Are there any questions? Could you raise your hand if you could have done that, or can now think you can now do it by yourself very quickly? All right, awesome. So majority of hands. So that's good. So because in your next, in your first problem set, that's the kind of thing you'll have to do. And over time, all the math will be similar, but it will get more and more complex. All right, and yes?
So do we know the use ahead of time, or you will also have to know you?
That's actually a great question. So we just did a lot of abstract math, and throughout the lecture we'll make this much more concrete, and we'll actually define where do you even get your u and v? Where does it start? The answer is it will start at some random small numbers. All your u vectors and v vectors will be small random numbers, and then that's actually what we'll talk about in the next slide. We'll actually go through how to use those vectors. All right, let's. Yes, question?
What are some other ways to get probabilities besides from softmax?
That's a great question. What are other ways to get probabilities other than softmax? There are a lot. Basically, you can define a very complex function that just takes as input one vector, and it takes the same function every time and tries to predict that. That could be a neural network with arbitrarily many layers and so on. In fact, one of the methods we'll talk about next will be a very large neural network to try to predict next words.
What are some advantages of using the softmax?
So I guess the advantage of using this extremely simple softmax is that really you will learn directly the word vectors. There's no other parameter in between the signal which is what words co-occur with other words, and the actual word vectors that you want to have the information of that be stored in. So we'll find actually other methods that are more complex, will be slower. This is also very fast because the only computations you make are directly relevant for the word vectors. Eventually we're going to want to train more complex models that do more things than just learn word vectors, and then we may need others. But in pretty much all subsequent work, we will initialize our models with these kinds of word vectors. So what if we now, we've computed our objective function, just the log probabilities at the top by just taking a bunch of inner products. In the beginning, this will basically all be pretty much random. Now we want to, we will call this our objective function, and if we minimize it, we can call it our cost function. Just for simplicity, throughout the rest of the lecture, we'll mostly minimize functions, and hence we'll use gradient descent. Whenever you're like, oh, Richard, but you forgot that, you should have actually maximized that, just put a minus in front of the objective function, and then we'll minimize it again. So it's basically the same thing. And so here, let's say we now know the derivatives. We computed the derivatives here, and we have our function. This is an extremely simple example of just standard gradient descent. I'm sure most of you are familiar with this, and I'm sorry to bore most of you. But again, what we'll do with gradient descent here in the simplest case is we'll just basically look as long as we make reasonable update steps in our derivatives into the right direction, and the actual value of the function doesn't change, or until it doesn't change very much, we'll basically update our old parameters. In this case, the old parameter here is our VC vector. And it will be basically minus a step size epsilon times the derivative that we just computed, which was UO minus the sum of the probabilities, the weighted sum of the other vectors. So this is, of course, if we only had a single data point. But in the original function, we actually summed over all the windows and all the time steps and all the windows around all these time steps. So throughout the next couple of lectures, we'll actually see how we can try to optimize this process. Instead of taking only a single example, we can take a small so-called batch, a mini batch of examples, and have a stochastic version of this. In the most simple case, if we had only a single window, we just compute one function, take the derivatives, and basically update our parameters that way in our word vectors. Any questions about that? All right. So I'm very happy to have seen all the hands of people being able to reproduce this. Basically, what I just described to you is the simplest way, but just like with the Cooccurrence matrix, it's not the way that will get you the best performance. In fact, the main problem is that we have this very large vocabulary, and in our objective function, we had, I guess now you can't see it, I need to work on my board constellations, but you had the sum over W from 1 to capital W, which is the entire vocabulary. So if you have 1,000,000 words, every time you want to update a single vector once, you have to compute a sum over 1,000,000 inner products. That's pretty inefficient, right? And so basically, that training will be too slow. So the idea will be, instead of having to take the normalization constant over the entire sum, we'll actually subsample here. And instead of having to do the softmax, we'll just have very simple binary logistic regressions. Yeah, so basically, this is very similar, eventually, to just focusing on mostly the positive correlations. And you will derive a similar model, but quite different in your first problem set, which we'll be due in 2 weeks. All right. Any questions about this? On the plus side, if this was boring you a lot, you'll be able to very quickly go through the first problem set. And if you have any more questions, you don't want to ask them now, we'll have office hours. In fact, my office hours will start today, so right after lecture, we're happy to chat more. All right, so why is this so cool? One of the interesting things is you can actually, these kinds of vectors are very, very good at encoding dimensions of similarity and dimensions of meaning automatically. So there are certain analogies that are very intuitive to people, and it turns out if you take the vectors of this kind of model, they will capture similar kinds of similarity. So for instance, if you take the vector of apple and you subtract the vector of the plural version of apple, apples, the resulting direction, the resulting vector, is actually very similar to when you take car and you subtract its plural, or family and its plural. So essentially, throughout a combination of these dimensions, you're capturing plurality. And what's even cooler is, remember how I described the Wordnet hierarchy, right? You basically had humans say, oh, I know that a panda eventually is like an animal and a placental and whatnot. Well, it turns out there's even some of these hypernym relationships are also captured. So if you take shirt and you subtract clothing, it's a very similar vector to when you take chair and you subtract furniture. So the model basically learned something by itself that we would have had otherwise, human experts sit down for a very, very long time and try to manually encode. And this one is a very popular one that made the press also. So, subtracting man from king is similar, gets a similar vector to subtracting woman from queen. All right, so in the last 15 minutes, I want to introduce briefly one model. The reason I can do that now briefly is because we went through all the gory details of the first model, and the second one is actually quite related. So there's one issue and basically contrast. So we talked first about the methods that used singular value decomposition, and these are all kinds of similar methods where LSA is a very popular one. From a couple of years ago, latent semantic analysis, basically also an SVD-based method, but instead of on word-word co-occurrences, it was on word document co-occurrence counts. And then we have here a plethora of other models, including the skipgram model, which is the word-to-vec model we just described and derived the first simple version of, and you'll look at all the approximations to make that model more scalable in your first problem set. So the first set of models has the advantage of pretty fast training if you don't have gigantic matrices, and it actually makes very efficient use of statistics, right? It tries to estimate directly the entire statistics instead of going through one window at a time, hoping to eventually capture the statistics that way. However, it's basically primarily used to capture word similarity. It's not very good at capturing these other kinds of notions of antonyms and different kinds of relationships between words. And it gives a disproportionately large importance to very small counts in SVD. On the other hand, you have the word-to-vec, which we just derived and described, which scales it scales with the corpus size, which isn't ideal, right? Ideally, if your corpus gets a little larger, you don't need to do a lot of extra computation. You can play devil's advocate here for both models. It also makes quite inefficient use of statistics, right? If I told you already, look, I have all these statistics, it can't use that. It has to still go through every single window of Wikipedia or a very large corpus. However, it is very good at generating improved performance on other downstream tasks. We'll look at grammatical analysis, sentiment analysis, and all these other methods, and it's actually very good for a lot of these other tasks. And can capture more complex patterns like the king-queen kinds of relationships much more cleanly. And so a model that Jeffrey Pennington, I and Chris Manning introduced is called GLOVE, Global Vectors. And it is essentially a similar idea to what we described here. We had the exponent before, and instead of that, we'll have here a squared loss. And again, we'll have two sets of vectors, one for the left side, one for the right. And you basically just try to minimize this function here. You're basically trying to minimize that the inner product between the left and the right vector will be close to the log probability of those two words actually co-occurring. So you can actually take the matrix, but you will go through one element of the matrix at a time. And that one element of the matrix actually captures all the counts directly instead of only one element. But it doesn't have to do a global computation on the entire matrix only. And just like before when I mentioned we actually need to cap certain function words, it also actually caps here these counts basically the probabilities to be basically have a max and then be flat. So this kind of model has very fast training. It's basically can be scaled to gigantic corpora. There's one corpus that is most of the internet. Forgot the word now. Common Crawl is the name. So Common Crawl is like a multi-terabyte data set, and this model can train on a single machine on that entire data set. And it gives also very good performance, even with small corpora, and also on smaller vectors. So it's statistically very, very efficient. So it's a good exercise for you at home to try to derive the derivatives here for this kind of model. That way, once you can do that, you know you're up to speed for this level, and then moving forward, you'll have an easier time. So here are some interesting results. So if you look at the nearest neighbors of the word frog, the most nearest neighbor is frogs, the plural, and then you get toad, litoria, and so on, all the way up to like some really rare Latin words for some pretty rare frog species. So this model basically learned that all these things are very, very similar and could be used in similar contexts. And what's more amazing is it can also do extremely well on these analogies. So you take the vector of basically, king, you subtract man, you add woman, and you'll actually end up at queen. And this is what these kinds of relationships and a data set to analyze how well models do was introduced by Mikolov just last year. So this is some pretty recent research that you're going to read if you read the original paper, and the models you derive in problem set 1 is a very recent paper. It's used in a lot of models right now. And here are some other interesting relationships that aren't just king and queen. So you can see that even emperor and empress, or duke and duchess, earl and countess, and heir and heiress, and so on, they actually all have a similar kind of vector offset. So it really captured that general phenomena. It goes as far as if you train it on more recent corpora, it also gets the relationship of a company and their CEO. So you have Caterpillar and Oberhellmann or something, have basically similar relationships. So it's amazing. And if you want to read more about the underlying sort of mathematical intuition of why these things happen, I can definitely recommend you reading Jeffrey's paper on the glove vectors. And this is exactly what I tried to describe up here, which is, wouldn't it be great if strong, stronger, strongest, or taken, or show, shown, showed, or whatever, different kinds of grammatical structures would also be represented in this vector space. And this is again what happens here. So slowest, slower, slowest has a similar pattern in the vector space to short, shorter, and shortest. So different superlatives and different adjectives and so on actually have similar kinds of vector representations. Yes?
So from these graphs, it looks like we're basically able to take relationships that we already know about and kind of confirm that these vectors seem to be similar to one another. Has there been any work in trying to discover new relationships? For instance, what if I don't know the CEO of Caterpillar? Can I use the information given from the other vectors with the same relationships to find the CEO?
That's a great question. I don't think people, in many cases, if you find the right expert around a certain domain, they will probably know this. But yes, in this kind of setting here, you could have actually tried to ask the model, given that I just told you that this guy is the CEO of this company, now tell me who's the CEO of this company. It will probably get it right. So yes, you could use that model to query unknown facts.
Try to do this to help information extraction?
Yes, in fact, these word vectors, the reason why we spend this lecture so much on it and we go through all the gory details is this will be used for a lot of the models in this class, and some of those will include information extraction. In fact, definitely next week we'll actually do named entity recognition, and we'll initialize our model that will be more complex and add more complexity on top of this kind of thing. We'll initialize it with these word vectors, and they help for named entity recognition. Yeah. Great question. Yeah.
You
Yeah, that's a great question. So we have here a bunch of, in some sense, cherry-picked, but in other ways, sort of reasonably picked ones. But where doesn't it work well? Well, it doesn't work well if you have multiple relationships. So maybe you ask like father, daughter, and now it might go to 1, but it can't go to n. I mean, it's just in the end, it's just simple matrix multiplication. There are things like take Japan, you subtract, or you basically look at Germany to something is like Japan to sushi, and I'll just give you bratwurst, and as a German I can tell you I don't like bratwurst, and I don't think that's that representative of German food, but that's the one thing it would give you, right? And so if there are multiple things, it has a hard time. Also, this is very corpus dependent, which I have so far sold you as a huge advantage, but it's also a disadvantage. What if you want to ask the currencies? So companies, countries and currencies is something that happens a lot, but what if now in your corpus, your currency changes? So, Germany had the Deutschmark before, now it has the euro. If your corpus is all old, it will still correlate Germany with Deutschmark and not with euro. And so there are issues like that, where if your corpus doesn't have the information, these kinds of vectors won't be able to capture it. Yeah?
Like, how much differential is the window size to the performance of these models?
It's very important. So it's definitely a hyperparameter that you should go over. I don't have the figure in my slides right now, but it's in the original Glove vector paper that actually has a very nice analysis of exactly what kinds of parameters matter. Does it matter to take only the left context versus only the right versus both of them symmetrically? Does it matter how large your context is? The learning rate. There are a lot of hyperparameters here that you could analyze, and several of those are in papers and now subsequent papers. Yeah, it's a great question.
Has any work been done on how these models perform for other languages such as maybe Mandarin or something like that, which has a much higher number of words or characters or anything like that?
So it's actually not true that Mandarin has more words than English. I believe English has the most words of any language because it has, French, English, Anglo-Saxon, Latin influences and so on. But yes, you can actually run these. There's a project from Stony Brook University, I think it's called Polyglot, that actually allows you to download word vectors in like 10, 20 different languages. That is the advantage, right? When you try to create Wordnet, you can spend a couple of decades before you have a reasonable taxonomy. Here, you can have a corpus like Wikipedia and you get something. Of course, there's also a problem if you have no corpus. If you have a language that isn't used by very many people, there's not that much written content about it, it's also hard to use these methods. And we'll run into those issues when we look at machine translation. But all right, so basically to wrap up the class, we have here major advantages of these low-dimensional word vectors. We'll actually, in the next lecture, be able to show you that we can now take these word vectors, initialize other models with them, and solve a lot of different problems with them. They'll be the basis for all the subsequent lectures and models. So if you did struggle with some of the equations we went through, definitely go through that and try to get up to speed. We can basically compute now from those eventually compositional representations for longer phrases and sentences and solve a lot of interesting problems. Thanks.